Creating a simple vertex shader. Let's make our first GLSL shader. Shoot along to this address. You should see a red wireframe box in the center of the screen. At line 26 we create the geometry for a box. You can define a box with 3 parameters, the width, height and depth, but you can also use 6 parameters, like here. Parameters 4 to 6 are the number of segments in the X, Y and Z directions. Here all are set to 10. Each side of the box will have 100 quads, a 4-sided polygon or 200 triangles, since each quad must be divided into triangles and a quad is made from 2 triangles. To see what is happening, I've set the wireframe property of a shader to true. The shader is only called for the edges of the shape this way. After creating the geometry for the box, we create an object called uniforms. A uniform is a way of passing variables from the control program to the shader. They're called uniform because for each screen render, their values will be unchanged. When creating a uniform using the ThreeJS library, it must be an object that has a single property, value. Notice here we have a uTime and a uRadius property. uTime is set using a clock instance to the elapsed time since the program began. The other uniform is the radius. The aim of our shader will be to mix between placing the vertex at a point that is radius length from the center and the modelled position of the vertex. Just to be clear, we now have a box. We're displaying this in a wireframe, and by dragging with the mouse we can rotate this around in 3D. Interesting, but so far it doesn't need a custom shader. For the material we're using the ThreeJS class shader material. This is designed for custom shaders. You might be wondering why anything is displayed. If so, well done. ThreeJS provides a default vertex shader and fragment shader if none is provided by the developer. Let's add our own vertex shader. In the vShader string at the start of the code, enter void main gl_position equal projection matrix times model view matrix times vec4 position 1.0. And in the options passed to the shader material constructor, add vertex shader vShader. Don't forget the comma. You'll see no difference. That is because the code we've entered is the same as the default vertex shader. Let's review it. Every shader program must have a main function. In GLSL, like C, a function is given a return type. Since this function does not return anything, we use the keyword void. A vertex shader must set the position of the vertex. It receives the model position as the variable position. This is provided automatically by the ThreeJS library. It is a vec3 type and we need it to be a vec4, so we add a 1. ThreeJS provides several matrices to the shader. They are model matrix, view matrix, model view matrix and projection matrix. The model view matrix is simply the model matrix multiplied by the view matrix. To transform the point from model space to projection space, we multiply it by model view matrix and then again by the projection matrix. So far we have nothing we couldn't have achieved with a mesh basic material, but we have a starting template. Let's have some fun. Slide up to the Vertex Shader code and enter uniform float uTime, uniform float uRadius outside the main function. Then enter float delta equals sine uTime plus 1.0 divided by 2.0. We're using the uTime uniform and the sine function to return a value between 0 and 1. The sine function returns a value between -1 and 1. The cycle repeats every 2 pi. Using the uTime uniform, the cycle will repeat roughly every 6.3 seconds. By adding 1 to the return value from the sine function, we have a value in the range 0 to 2, which we divide by 2 to get a value in the range 0 to 1. Now enter vec3v equals normalized position times u radius. vec3 pos equals mix position v delta. And in the GL position assignment line, change position to pos. Your box blends into a sphere and back to a box in a looping cycle. Let's look at how this is achieved. Remember that a vertex shader is principally there to set the position of a vertex. It does this by applying the model view matrix and the projection matrix to a homogeneous coordinate, a coordinate that has an additional fourth parameter, usually set to 1. This is so that 4x4 matrices can be applied and positional changes will occur under matrix multiplication. But let's not overworry that. The important thing is we need to set the GL position property. If we simply use the model position for this, then we get a box that we can rotate using the orbit controls object. How would we take the model position and place this at the outside of a sphere of radius specified by the uniform u radius? First we take the current position and treat this as a vector. We normalize it. That is, we set it to a vector of length 1. Imagine a vector extending from the origin 0, 0, 0 to the position. This is converted to length 1 and then multiplied by the u radius property. Now it's on the surface of a sphere of radius u radius. Then we use a delta value that uses time and the sine function to create a variable that moves smoothly between 0 and 1. We use this value to mix between the position, the modelled location of the vertex, and the calculated position v. That is where a vertex that is projected onto a sphere of radius u radius would be. The result is a breathing box. Try reducing the range of movement so it never goes more than a quarter of the way to being a sphere. Pause the video now and give it a try. Easy one. Just divide delta by 4. If this seems a little too slow, then multiply the u time value at line 6 by a factor. Before we go too far into vertex shaders, it would be nice to add some lighting. 3D benefits hugely from lighting, and the ThreeJS library includes lots of light types. This video comes from my Packt course. Find the course on Udemy by following the links in the description.